Assalamu alaikum dear students, hope you are all doing well and safe. Welcome to the practical course of circuit analysis. Here's your lab instructor Nashita Alwas. Agenda of this experiment includes 7 different sections: lab objective, equipment needed for the experimentation, theoretical background of the experiment, software implementation, results and discussion part, conclusion, and the task assigned. The title of today's experiment is to study the response of series resonant circuit using NI Multisim software. Equipment needed for the experimentation is NI Multisim software installed on the personal computer. Firstly, we have to look at the theoretical background of this experiment. What is resonance? Resonance is a tendency of a system to oscillate. As we have already studied about this, if we will take the example of a swing, then we will apply the force to this swing. So the frequency of the swing and the natural frequency of the swing means the two elements we will consider in this phenomena. If the applying swing frequency force will be equal to the natural frequency, at this time we have the phenomena of resonance. What is resonance in electrical circuit? Resonance is the phenomena at which response of the circuit is maximum for a given particular frequency. This response will be seen in the electrical circuit because of the capacitor and inductor. Both the elements have the ability to store the energy. Due to this, even if we remove the voltage source, the inductor will continue to supply current to the capacitor, and through this current, capacitor will charge. And later on, this capacitor will act as a voltage source and it will gain some supply energy back to the inductor. So in this way, energy will be transferred between the capacitor and inductor. Rate of this transfer energy depends upon the value of L and C. Because of this transfer of energy, we will see oscillation in the circuit. Resonance in the RLC circuit is the phenomena in which capacitive and inductive reactive terms are equal in magnitude, thereby resulting in a purely resistive impedance. These phenomena, basically resonance phenomena, are useful for constructing filters in many applications. So what is series resonance circuit? Series resonance occurs when the supply frequency creates zero phase difference between the supply voltage and current, producing a resistive circuit. Series RLC circuit will be used in the filter network to either select or reject the AC frequencies. Here we have the series RLC resonant circuit. We will apply the supply voltage with the tunable frequency, and we have 3 components R, L and C. Each have their own resistance. The resistance of capacitor and inductor is known as the reactance, and when we apply the voltage, current will flow in the circuit, and current will remain same across each component in the circuit because it is the series circuit, but voltage drop will be different across each component. So if we will apply the alternating voltage source across the circuit, then we have the resistor component first, and we know that the effect of the alternating source on the resistor is 0. So we will take the resistor at the x-axis as the reference, and we will draw the capacitance reactance and the inductor reactance towards this reference. And we have already studied about that the reactance of the inductor will have the phase angle shift, means the leading angle shift with the resistor value. So XL has the positive value, leading value towards the resistor. And we have already studied about the reactance phenomena of the RLC circuit. Reactance is basically has the lagging phase shift with the resistor value. So when we have the lagging phase shift with the resistor, so XC will be occur in the negative portion. So we can see that the XL and XC are opposite towards each other, because XL will be occur at the leading power factor or the angle, and XC will be occur at the lagging angle. So we have already talked about the XL value, which is equal to 2 pi FL, means it will be dependent upon the value of the inductor and the frequency in the circuit, and XC value will be equal to 1 by 2 pi FC. And resonance in the circuit will be occur when both the XL and XC will be equal. So let's see how we can analyze the resonant frequency in the RLC series resonant circuit. If we will consider XL equals to XC, so XL equals to 2 pi FL and XC equals to 1 divided by 2 pi FC. So F square equals to 1 by 2 pi FL, not FL, basically 1 by 2 pi L multiplied by 2 pi C, which is equals to 1 divided by 4 pi square LC. Then if we will take the under root of this terminology, then F means the resonant frequency will be equals to under root 1 divided by 4 pi square LC. So the resonant frequency equals to 1 divided by 2 pi under root LC. Total impedance of a series RLC circuit is basically dependent upon the value of the resistor and the reactance. And we have two terms in the reactances phenomena, inductive reactance and the capacitive reactance. So the total impedance of the circuit will be equal to R plus jXL, means the reactance of the inductor and the reactance of the capacitor. And we know that the inductor reactance and the capacitor reactance are basically opposite towards each other. So if we will consider the value of XL equals to 90 and value of XC equals to 90, so both are opposite towards each other. So C total equals to R plus J XL minus XC. And if we will take 90 as XL and 90 as XC, so 90 minus 90 equals to 0. So we have the only Z total, which is equals to the value of R, and that point is basically called as the resonance. And at resonance we have equal amount of XL and XC. When we have the equal amount of XL and XC, the impedance will be reduces to the value of resistor, and when we have the less amount of resistor or the impedance in the circuit, so the current will be maximum, and we can find out the value of current at the resonance point by using the formula of Vs divided by C total, and we know that C total will be equal to the value of resistor in the circuit. For the determination of the impedance in the series RLC resonant circuit, we have to analyze the XC and XL values at different frequencies. We know that at one point when capacitor is basically charging itself, it means that the inductor giving voltage towards the capacitor. When capacitor discharging itself, it means that inductor basically storing charges and gain voltages from the capacitor. So at that point when we have the greater voltage at the capacitor, inductor has the less amount of voltage, means both terms are opposite towards each other, and they have basically 90-degree difference with respect to the resistor value. Capacitor voltage is basically the lagging voltage with respect to the resistor voltage, and the inductor voltage will be the leading voltage with respect to the resistor voltage. So if we will analyze the values of XC and XL at varying frequency, at a lower frequency and or at the frequency 0, XC will be equals to infinite, as we know that XC equals to 1 by 2 pi FL, and if we will put the value of 0 at the frequency, so we have XC equals to infinity, XL at that point equals to 0. So it means capacitor will behave like an open circuit and we will not find out any type of current across the capacitor network. And if we will analyze frequency response or the response of the series resonant circuit at frequency infinity, so the inductor have infinite times of the reactance and it will be act as an open circuit. So we have different amount of voltages or current across the different values of the frequency. When we have the less amount of frequency, then we have also little amount of resistive and reactive element in the network, and we have when we have the equal amount of resistive and reactive term, then we have less amount of current in the network. But if we will cancel out the reactive term in the network and we have only the resistive term, then the current will be increasing stage in the waveform. Here we have the impedance waveform of series RLC resonant circuit. We can analyze that at low frequency we have capacitive reactance greater than the inductive reactance, and at the high frequency we have inductive reactance will be greater than the capacitive reactance, where there is some point where the capacitive reactance basically equals to the inductive reactance. At that one point, basically where the inductive reactance equals to the capacitive reactance equals to the series resonance value. So at the resonance frequency point, inductive reactance will be equals to the capacitive reactance, and when the inductive reactance will be equals to the capacitive reactance, they basically cancel out each other's effect, and we have only the resistor as the impedance term. So when we have only the small amount of resistor as the impedance in the network, then our current in the circuit will be at increasing stage at this point. So we can analyze the current waveform in the circuit at the lower frequency. We have the reactive and resistive term, so we have the less amount of current, and at the higher frequency also we have the resistive and reactive term, so we have the less amount of current. But at the one resonant particular frequency, we have the equal amount of resistive reactive terms of the capacitor and inductor, so they basically cancel out each other's effect and we have only the resistor. So when we have the less amount of impedance in the circuit, current will be the maximum, and we can analyze this response in the graph of the current and voltage also. At the resonant frequency, when we have only the resistive element as the impedance, we have greater amount of the current and voltage at that point. So we have learned that resonance in the circuit will be occur when the inductive reactance will be equal to the capacitive reactance. When both reactance will be equal, so they basically cancel out each other's effect, and we have only the resistive component, means the impedance of the circuit will be very minimum, and so the current will be maximum at the resonance point because impedance is in a very minimum quantity. And when we have the only resistive element, so the voltage and current are in phase, and we have the phase angle between voltage and current is 0 degree, and we know that power factor is basically equals to cos phi. When we have the angle 0 between voltage and current, so cos phi will be equal to 1, and we have the maximum power transfer across the circuit. And we have already studied that resonance in the circuit will be occur when we will transfer the maximum power across the network, and maximum power occur when Xc equals to the Xl. Resonant frequency is the frequency at which inductive and capacitive reactance of a series circuit are equal. When we have the equal amount of inductive and capacitive reactance, then they are basically cancel out each other's effect because the current of the inductive and capacitive terms are equal and opposite in phase. So when the inductive and capacitive reactance cancel out each other's effect, then we have the only term resistor in the circuit. So our impedance is in a very low value because it will be equals to the resistive element only. So current in the series resonant circuit will be maximum, and when we have the maximum current in the series resonant circuit, the frequency is basically known as the resonant frequency. And at the resonant frequency we have only the resistive element, so we know that for the resistive element we have current is in phase with that voltage of the circuit, so the power factor of the circuit will be the unity power factor. Resonance in RLC circuit will provide the some kind of selectivity for the given particular frequency. This principle is used in radio communication for selecting the particular channel. Let's say you have FM receiver and you want to tune your FM receiver at one particular frequency or one particular channel. So now let's you want to change our channel. We used to change the knob of the receiver. Eventually we are changing the capacitor value in the circuit. So in this regard, waveform will be changed, means the waveform of the current in the RLC circuit will be changed and it will be shifted to another frequency. So we will be able to change the channel of the receiver. To simulate the series resonance circuit, we have to move towards the NI Multisim software. So firstly, I will place all the components of the series RLC based circuit. Moving towards place components section and then power sources, then I will choose AC power. And after this, I will choose ground block. Then I will move towards the basic section and pick the resistor of 40 ohm and click OK. Then I will move towards the capacitor section and pick the capacitor of 0.1 microfarad and click OK. Then I will basically move towards the inductor section and pick the inductor of 30 millihenry and click OK. So the component placement section is over. We have placed all the components on the window of NI Multisim software. And now I will connect all these components in a series combination. Resistor, inductor, rotate this capacitor. Then I will connect the battery with the resistor, then inductor. Then I will connect the inductor with the capacitor, then capacitor with the battery, and connect ground block. Now my circuit is completed. For the analysis of this AC circuit, I have to move towards the simulate section and then analysis and simulation. Then I will basically move towards AC sweep section and pick the start frequency of 1 kilohertz basically, and pick the stop frequency of 10 kilohertz, and number of points per decade will be equal to 1000. Then I will move towards the output section and pick V3 voltage basically across the circuit and click on add, and then I will basically run the simulation diagram. So here I have the proper results of series resonant circuit. So here I have the proper results. We can analyze the current of the series resonant circuit. We can say that before the resonant frequency, we have the less amount of current. And when we have the less amount of current, circuit will behave like an inductive circuit. So that's why here at the left hand side of the resonant frequency, we have the phase shift occur. So circuit will behave like an inductive circuit because current is basically in the increasing stage. And after reaching at this point, means resonant frequency point where the impedance of the circuit basically equals to the resistive element only, and we have the capacitive and inductive terms also, which is basically equal in terms and opposite in phase shift. That's why they are basically cancel out each other's effect, and at the end we have just the resonant frequency occurrence where the impedance of the circuit will be equal to the resistive element. And when we have the less amount of impedance in the circuit, we have the maximum amount of current in the circuit. So at the resonant frequency means at this point we have basically the less impedance, means the impedance which is equals to the resistive component only. So the current at this point will be maximum. As we have an increment in the resistance of the capacitive or inductive term, our current is basically moving towards the downward position. So before resonant frequency, circuit will behave like an inductive circuit, and after the series resonant frequency, circuit nature is basically the capacitive nature. So this is how we can implement the series resonant circuit, basically the series RLC resonant circuit on NI Multisim software. From this experiment, we have learned the analysis of the response of the series resonant circuit using NI Multisim software. Tasks assigned for this experiment are listed in this slide. You have to complete these tasks before the commencement of your next week lab. Write down your experiments in your manual and share the work with me through Microsoft Teams. This is all from my side. You are welcome to ask any question related to this topic. Thank you very much for listening to me. Good luck. Allah Hafiz.